Our next section is stoichiometry with excess limiting and percent yield. This is question number 13 through 16 in your classwork. Okay, number 13 says, how many grams of KClO3 must be decomposed to obtain 3.50 grams of oxygen? Our first step is to get a balanced chemical equation. Remember that potassium chlorate decomposes into KCl and O2. Let's go ahead and balance that with a 2 in front of the KClO3 and KCl, and a 3 in front of the oxygen. And every time I have a stoichiometry problem, I find it much simpler if I can just write down what I'm looking for underneath the question. So underneath KClO3, there's a question mark grams. Underneath the oxygen, there's a 3.5 grams. So if I want to try to get from one compound to another using a balanced chemical equation, I need to know the mole-to-mole ratio of, in this case, oxygens to KClO3s. But 3.5 grams is grams, not moles. So I'm going to have to convert those 3.5 grams of oxygen into moles of oxygen. So oxygen, since it's O2, weighs 32, let's make that 32.0 grams for every 1 mole. And that'll give me the moles of oxygen. But I don't really want the moles of oxygen. Of course, I want the moles of KClO3. So one more step says that for every 3 moles of oxygen, I've got 2 moles of KClO3. And so that's the moles of KClO3, but I don't actually want that. I want the grams of KClO3. So one more says for every 1 mole of KClO3, we have a certain number of grams off the periodic table. So you're going to have to look that up off the periodic table. K is 39.1 grams, Cl is 35.5 grams, O3 is 3 times 16.0 grams. Make sure you're using at least one place past the decimal for potassium, 39.1, not 39 even. Add all of those together and you end up with 122.6 grams. So that's the mass off the periodic table for KClO3. Multiply it all, 3.5 divided by 32 times 2 divided by 3 times 122.6. Overall gives you 8.94 grams of KClO3. Number 14. How many grams of NH3 will be produced when 14.0 grams of hydrogen reacts with 84.0 grams of nitrogen? First thing we want is a balanced chemical equation. So NH3 is going to be produced when hydrogen reacts with nitrogen. So hydrogen and nitrogen are actually going to go on the left-hand side, or the reactant side of a reaction. NH3 will go on the right, the product side. Let's balance that to get the hydrogens and nitrogens both balanced, and write down your information. Underneath NH3 is question mark grams, underneath hydrogen is 14.0 grams, underneath nitrogen is 84.0 grams. Okay, this is called an excess limiting problem, because one of these, hydrogen or nitrogen, is in excess, and the other one is limiting you from how much NH3 you can make. But we don't really know which one's which. So what we're going to do is, starting with 14 grams of hydrogen, how much ammonia will be produced? And then, starting with 84 grams of nitrogen, how much ammonia will be produced? Whichever one is the smaller answer is the one that's actually possible. So for hydrogen, starting with the 14.0 grams, and hydrogen, since there's 2 of them, weighs 2.0 grams for every 1 mole. The mole-to-mole ratio is 3 moles of hydrogen for every 2 moles of ammonia. I'm actually looking for grams of ammonia, so 1 mole of ammonia weighs 17.0 grams, 14 for nitrogen plus 3 for the hydrogens, and that will give me a total of 79.3 grams ammonia. So if I had 14 grams of hydrogen and plenty excess nitrogen, I would make 79.3 grams of ammonia. What about nitrogen? If I started with 84.0 grams of nitrogen And nitrogen is 28.0 because there are 2 of them in N2 for every 1 mole. Then there's 1 mole of nitrogen from the balanced equation compared to 2 moles of ammonia from the balanced equation. And then 1 mole of ammonia happens to weigh 17.0 grams. This is going to be equal to 102 grams of ammonia. So what this means is, if I had 84 grams of nitrogen and plenty excess hydrogen, I would make 102 grams of ammonia. So which ammonia can I actually make? Well, it looks like 79.3, because I don't have plenty of the other. I only have enough hydrogen to make 79.3 grams of ammonia. So I could not make 102 grams of ammonia. It's not possible. So my final answer is the smaller answer, 79.3 grams of ammonia. Number 15, how many grams of water can be formed from a mixture of 100 grams of hydrogen and 100 grams of oxygen? So one of those is going to be in excess and one of those is going to be limiting. Start with a balanced chemical equation. Hydrogen plus oxygen makes water. Let's balance that with a 2 there and a 2 there, and write down what you're looking for. How many grams of water? 100 grams of hydrogen, 100 grams of oxygen, and we're going to do 2 separate problems. One with the hydrogen and the other with the oxygen. Whichever one makes the smaller amount of water is the one that is possible. So for hydrogen, starting with 100.0 grams, I'm going to write H2 here so we don't forget which one we've got. 2.0 grams for 1 mole. The mole-to-mole ratio says 2 moles of H2 for every 2 moles of H2O. But I'm actually looking for grams, so I'll have 1 mole of H2O is 18 grams of H2O, which gives me 900 grams of water. If we're starting with the 100 grams of oxygen this time, I'm going to write O2 here so we don't forget. That's 32.0 grams of oxygen for every 1 mole, because there's O2. In the balanced equation, 1 mole of oxygen gives you 2 moles of water. But since we're actually looking for the grams of water, one more step. 1 mole of water for every 18.0 grams of water, which gives me a total of 112.5 grams. So if I had plenty of oxygen and 100 grams of hydrogen, I would make 900 grams of water. But I can't make 900 grams of water because I don't have plenty of oxygen. I only have enough oxygen to make 112.5 grams of water. So I'm only going to be able to make 112.5 grams of water. It doesn't matter if you have 3 packages of ham and 25 pieces of cheese. If you only have 2 pieces of bread, you can only make 1 sandwich. So the second part of number 15 says, how many grams of the excess reactant is left over? Let's look at that again and remember which one was the excess reactant. We said with 100 grams of hydrogen, you could make a total of 900 grams of water. With 100 grams of oxygen, you could only make a total of 112.5 grams of water. So the one that's in excess is the one that could make more water, so that's going to be the hydrogen. The hydrogen is the excess reactant. This 900 grams of water is not possible. You never actually made that. It's just if we had had enough oxygen, but we didn't. So we have to figure out how much of this 100 grams of hydrogen is left over at the end. You can start with either the 100 grams of oxygen or the 112.5 grams of water. It doesn't actually matter. I'm going to start with the 100 grams of oxygen. It makes more sense to me. So 100.0 grams of O2. But this time, instead of figuring out how much water, we already know that's 112.5, I'm going to figure out how much hydrogen is used. So oxygen is 32.0 grams for every 1 mole. And referring to that balanced equation from earlier says that 1 mole of oxygen needs to react with 2 moles of hydrogen, and that 1 mole of hydrogen only has a mass of 2.0 grams. So 100 divided by 32 times 2 times 2 ends up being 12.5 grams of hydrogen. Now that's 12.5 grams of hydrogen used with the 100 grams of oxygen to make water. That's not how much is left over. We started with 100 grams of hydrogen. We used 12.5 grams of hydrogen. What's left over is 87.5 grams of hydrogen. Alright, last one in this section. A chemistry student. Preparing copper metal by the reaction of 1.275 grams of copper 2 sulfate with zinc metal, it isolated a yield of 0.392 grams of copper. What was the percent yield? First things first, balanced chemical equation. We had a piece of zinc metal reacted with copper 2 sulfate, and we know that that's going to produce copper metal with zinc sulfate. This is an already balanced chemical equation, 1:1:1 ratio. We started with 1.275 grams of the copper 2 sulfate with some unknown amount of zinc. We ended with 0.392 grams of copper. What we're trying to figure out is how close were we when we made that 0.392? Were we right on the mark? Did we get too much? Did we get too little? So the stoichiometry problem is actually starting with the 1.275 grams and figuring out how much copper we were supposed to make, and then we're going to compare it to how much copper we actually did make. So 1.275 grams of CuSO4. Now let's see, copper 63.5 plus sulfur 32.1 plus 4 times oxygen, which is 64, makes a total of, my calculator out here, 159.6 grams of CuSO4 for every 1 mole. The next is the mole to mole ratio. 1 mole of CuSO4 for every 1 mole of copper. I'm actually looking for the grams of copper, so one more step says 1 mole of copper for every 63.5 grams of copper off the periodic table gives me a total of 0.507 grams of copper. That's how much copper I was supposed to make. 0.392 is how much copper I actually did make. So what is my percent yield? Percent yield is the experimental amount over the theoretical amount times 100. The experimental amount in this case was 0.392 grams. That's how much I actually did make. The theoretical is the 0.507 grams, which is how much I was supposed to make from the given original amount, times 100 gives me 77.3% yield. And that's the last one in this section.